Fear not, my friends. This will be my greatest performance.
The existence of the bow and arrow can be traced back to the Stone Age, about 20,000 years ago. Since then, the bow and arrow blueprint has seen few major modifications. A semi-rigid but elastic material forms an arc with a high tensile cord that attaches to both ends of the bow. The mechanics of this simple system are elegant and straightforward. The compound bow is a complex modern bow that uses a system of cables and pulleys to bend the limbs. It was invented by Hollis Wilbur Allen in the 1960s. To make the bow, he sawed the ends off a traditional bow and then added cams to the end of each limb. Both of the cams have one cable attached to the opposite limb, and when the string is drawn back, cams turn, the limbs of the bow flex, and add energy to the bow. Cams are eccentric, so they act as levers and allow for archers to hold the bowstring in the maximum draw without too much strength, which is known as let-off, and allows for more accurate and less strenuous aiming. This system can also be described by Hooke's law. In this clip, I demonstrate the relation between force, as measured by a spring scale, and distance. As the distance increases, the force necessary to pull the drawstring back increases, which we know to be proportional to the force constant as stated by Hooke's law. Now that I'm editing this video, I can see that the spring scale in the previous clip was not in frame the entire time. So here you can observe how the spring scale increases to a point and then decreases rapidly. And here's a close-up of the spring scale. This is a graph generated by Randall Peters in a study of the nonlinearity of the compound bow. As we know, the area under the curve of a force versus displacement graph is equal to the total work done. Note how force increases with displacement up to a point and then gradually decreases. To understand why this happens, we need to understand how cams work. This is an explanation of how the draw force changes as the drawstring of a compound bow is displaced from its original position. This is the point that the tension force of the drawstring is applied to this pulley, and this is the axis of rotation. At rest, the distance between these 2 points is relatively small. As the compound bow drawstring is pulled, you can observe that the point of application of the tension force grows further and further away from the axis of rotation. At this point, the distance between the axis of rotation and the point of application is the greatest. As you continue, it crosses over a breakover point and becomes much easier to pull. This is what it looks like for a natural drawback of the drawstring. And that's all the time I've got for today, folks. I've got exams to study for and labs to do, so good luck with finals.